Hello everyone, hope you're having fun studying for exams. I heard that your geotech exam is on Friday, so here I'm recording another video. This will specifically be on like horizontal loading of piles. Now, the reason I'm doing this is because apparently horizontal loading on piles was actually included in the course this year, where in my week 9 tutorial, the one on piles, I think I said something along the lines of, don't worry about it, it's not in the course, but it is in the course, and so you should study it because the lecturer specifically mentioned in a forum post that it's included in this year, in this course. So I would say there's like a high chance that you'll see it come up in the exam, probably something in the ballpark of like 90% chance. In terms of how I'm recording this, I'm going to try a slightly different style. So the software that you can see right here is Bluebeam. I made my notes in Notewise, which is the program that I normally use to like scroll through the notes, doodle and stuff like that. But I'm just gonna try a new style. I'm gonna use Bluebeam. It's basically just me flicking through the PDF, and yeah. So because I'm not really gonna do much working out, I'll see if Bluebeam's any good. So yeah, basically what you can see here is like a little map. Right, so this first page is a little map of what you can expect to see in this particular topic. So this falls under the general topic of piles, but whereas before we had a, okay, I can see Bluebeam already lagging. We had a pile like this, and we only dealt with vertical loading. All right, so if we call that something like V, that'd be a vertical loading, right? But now we're also dealing with something like H. So H is the horizontal loading that's on the pile, right? So this can arise from any sorts of things, right? So if you imagine that's the ground, right, and then your pile's underneath your building, there could have been, for example, a column from your building which was at an angle. I'm not really drawing this. Let's flip that. So we go alignment, flip. There could have been a column from your building which was raked, which means it's diagonal, and so therefore the forces coming through that column transfer like a diagonal load, and so you've got this horizontal component to it. That's just an example of where you can expect to see this in real life, like horizontal loading on the top of the pile. Okay, so what you can see here is depending on the like basically what's on the top of the pile, we have two different scenarios, right? We have one where it's got a free end, okay? So sometimes that horizontal load, by the way, can have an eccentricity. So we call this dimension from the ground to where the load's applied. We call that eccentricity E, right? And then we're gonna call this normal length, the length of the pile, L, right? So that's the same as what convention we've been using for piles. As well as lowercase d, which is the same as the convention for vertical loading of piles, okay? So basically, yeah, this horizontal loading, if it's like that, or even if the horizontal load is applied without an eccentricity from the ground, yeah, that's basically one scenario. That's where you have a free head, right? But sometimes the top can be socketed into like a block of concrete or something. And this basically now becomes a fixed head pile. And in terms of how it behaves from like a 1300 perspective, right? Imagine you've got like a cantilever beam that's going downwards, and it's got a fixed end at the top. That's basically how it's going to behave. So we're going to see how this manifests in terms of two things. The ultimate capacity, which just means how strong it is horizontally, how much force it can take, and the lateral deflection and rotation, okay? So lateral deflection and rotation just refers to how far has this, I can see the problems with using Bluebeam, but how far has this deflected, right, from the ground, from say this starting point here, to over here. We call that rho, so that's your lateral deflection at ground level. And that angle that it's been rotated, let's say this angle from here to here. Oh, what have I done? The angle from here to here, right? Let's draw that. That's theta, so that's the angle that is deflected. Okay, so we're going to consider deflection too. All right, so I want to talk about different failure modes, right? So with those free head piles, where it's free to rotate at the top, basically there's two modes of failure. The first one is where the soil fails, right? So you can imagine the soil is too weak and then fails kind of like sideways and bearing. And the other type, this one, is where there's a plastic hinge which is developed in the pile. So what that means is basically if you treat the reinforced concrete pile as like a plastic object, which means it basically has like it forms its own point of rotation here. If you treat it like that, right, and then that happens, basically this like failure mode is governed by some maximum bending moment, which is your yield moment, okay? Whereas this one has no limit. Hold on. Wait, basically, let's do this, right? So, stress strain graph, right? So this is a material property kind of thing. And probably what you've seen a lot of is stress or sigma and strain on the x-axis, right? So this would be a normal material curve. But instead of stress, if we're talking about it in terms of a moment, right? The idea is, if we consider concrete as a perfectly plastic object, pretend it's like steel, right? The idea is that there's some kind of yield moment, right? Which will cause it to plasticize, okay? That's what I'm trying to say. All right. Okay, so that's free-headed piles. For fixed-headed piles, the first two failure modes are similar, except, so the first one, basically the whole thing just shuffles across, right? So the deflection shape looks like that, rather than allowing some kind of point of rotation. For the second type, the plastic hinge will develop at the interface between the concrete block and the top of the pile, basically. And so yeah, that's where the plastic hinge will develop. And then for the second mode, there's actually two plastic hinge points. So it'll form this like dog leg shape, dog bone shape, I guess. Okay, so anyway, that's just like theory, but let's see how it's actually applied, because that's probably more important. So essentially, when you're doing the strength calculations or ultimate capacity, this is the tree diagram, right? So the first thing you want to consider is whether your soil conditions are undrained or clay, or if it's drained. So that's like sand, right? The next thing you want to think about is whether you've got a free head at the top or a fixed head at the top of the pile, okay? And then there will be the different failure modes, which I talked about, that you have to check for, right? And the idea is that you'll find some kind of HU, right? So HU would be the maximum horizontal force that can be applied, right, in the ultimate condition for mode 1, right? And you'll find, you know, HU for all of these modes, right? So depending on whether you're looking at the free head case or the fixed head case. So let's just say we're looking at the free head case, right? The idea is we need to check these two values, and then essentially what you end up taking is the minimum between these modes, okay? And the same goes for if you're looking instead at the fixed head case, right? You would check all three of these and then do some little checks at the end. Okay, and this is similar for drained, but the formulas are different, okay? But the theory is the same. Okay, and then we'll talk about serviceability, or how much it rotates and deflects at the top, at the ground level later. Oh, but essentially that's a function of whether your soil has a consistent elastic modulus, or the elastic modulus gets stiffer as you go deeper into the ground. So you'll find out later. This is for OC clays, or over-consolidated clays is the first case, and this is NC clays and sands follow the second set of equations basically. And then you figure out whether you have to work it out for your free head or your fixed head at the top. Okay, so the reason why I've decided to use Bluebeam, by the way, right, is because Bluebeam has a nice splitting function. So I'm viewing this PDF, right, and I can split it like this. Look at that. So I'm going to adjust these windows a little bit so you can see where we're up to as I'm talking about it. Okay, so I'm going to keep that on the right hand side, that window on the right hand side as is, and scroll down with the left one. Okay, so here's the first page. We're talking about ultimate capacity at the moment. Okay, and we're talking about undrained conditions, and we're talking about free head piles first, and then we're talking about mode 1. Okay, so you can see how we're following this tree diagram as you can see. So for undrained conditions, the question will give you your material properties or your undrained cohesion, right? So using that information, we're going to solve for two things. We're going to solve for the ultimate horizontal force that your pile can take, and we're going to find the max moment. And I'll explain later why we need to find the max moment. Okay, so the steps in order are: 1, you find your slenderness ratio, so that's the length of your pile divided by the diameter. Okay, the next thing you do is you find your embedment ratio. So no, that's the wrong word. Sorry. I think they're called L to D, the embedment ratio, but it's kind of like a slenderness ratio. So E to D is your eccentricity of that horizontal force divided by the diameter, right? And this can be 0 if H is applied at the ground. If H was there, for example. So if I set this to blue, hopefully that's visible. Okay, that's definitely visible. All right, so if H was there, then E is 0, okay? There's also a special case, right? Which is that if your H is applied at ground level, but you have a moment that's also applied, like a known moment, then you can work out your eccentricity with this formula as well. Okay, so this would be the equivalent of applying H up here, right? And then it'd be like as if you're eliminating your point moment. Yeah, that's the idea. Okay, and then you basically want to find this lambda s value from the graph on the right. To be honest, I don't know why it's called lambda s. And sometimes it's like inconsistent because like throughout these notes, there'll be lambda s, lambda l, and then this sometimes it's just not even named. So I just invented some names for them, but it will always be lambda something. Yeah, so but the idea is we're finding lambda s, okay? And that's from this graph, okay? So what you need to do is you need to find the embedment ratio or the L to D ratio. You need to find your E to D ratio, right? So let's just say it's 15. So let's say this one you worked out was 15. Let's say you worked out this one as, I don't know, 20. Okay. What you would do is you'd go from 20 up to the 15 line across to find lambda s, and in this case it would be like 30, right? So that value would be 30. You plug in your CU, which you know from the question. You plug in the diameter, square it, the diameter of the pile, and that will give you your horizontal ultimate force or whatever. All right, next thing you got to do with that information is you need to find M max, the maximum moment that's applied. It's actually easier to see on this graph here, right? The idea is that F is this distance. To be honest, right, you actually don't need to know this information. I just drew it for context, right? Like you don't need to draw out all these diagrams, right, versus depth, right? But I think it's good to know where these numbers come from, at least somewhat. You can backwork it if you like and try to figure out how they got the moment equilibrium and whatever. But if you don't care, if you just want to pass the course, these are the steps you follow, okay? So to find M max, you find the value for F first, which is the length, the vertical length of that distributed load. And you got to find G, which is the vertical length of that portion of the distributed load. So these are related to each other. So you find F first, and then using F you find G, and then using G you find M max. Okay, so that's how you find the maximum moment which is applied along your distribution. Okay, so if you're interested in why this is, right, and I know most of you guys aren't, but you have to think of like soil like a bunch of springs, okay, and the spring supports, right? So you've got these like continuous line of spring supports, and it's resisting this bending moment, right? And so yeah, you get like a very funny like moment distribution. And then there's also this portion due to like soil cohesion, which makes it so that the soil's in tension. And so we don't give it a reaction. So here you'd almost have like a negative reaction at the spring, so it'd be in tension. So we don't consider that portion due to the soil's stickiness, clay's stickiness. Okay. Anyway, mode 2, right? So you're always given my in the question. That's the yield moment, or fuck, I deleted it, didn't I? Yeah. Anyway, remember that little graph I drew of the material properties, right? The idea is that they tell you the limit of how much moment can be applied on your concrete pile before it yields, okay? And that's relevant because we're going to need it in this upcoming graph, right? So we're checking for the pile yield failure mode, okay? So now we're shifting to here. All right. You want to find the E to D ratio, right? So that's the same as mode 1. So we might already have that number, but we're going to need it for the graph. You'll see in a second. Number 2, you find my divided by cu times du cubed. Now, this seems like a pretty random ratio to find, but the reason is that's just how the graph is presented. So you have to find these things, right? So that was that, and let's just say that was 100. Let's say this ratio is 100. Let's say that E to D we found was, I don't know, 30. What you do is you go to this graph, you go from 100, go to 30, the line, and then you go left, and then you, like, it's logarithmic, so it's a bit annoying. But you have to figure out what it is. So that's 2, that'd be 3. So it'd be like between 3 and 4, something like that. So 3.2, or I don't know, whatever you want to choose. Or you can find it from this formula. Now, not all of these graphs give you a formula, but this particular one does for the mode 2 failure. So depends whether you want speed or you want to be like incredibly accurate, then you can use this formula if you don't want to use the graph. But that one's lambda L, right? And then so your horizontal capacity for free head under mode 2 failure is given with this equation, right? Okay, so now the final checks, right? The idea is that we have, we're checking a free header pile that's undrained. These are things that we knew before we even launched into the equations, right? This is just something you figure out by looking at your scenario. What you have to do is you have to figure out from mode 1 and mode 2 what the minimum was, right? And if the first mode governed, you have to do a sanity check basically to make sure the maximum moment that was applied. So if I scroll up, this formula, right? The maximum moment that was applied from your external bending moment, you have to check that's less than the yielding moment, right? And if it's less than the yielding moment, we're still in the elastic range of our concrete pile. Okay, so if this is, again, M versus, I'm going to do it as strain. Have caps lock on. M, and let's say that's strain. All right, so that's our plastic plateau in our material curve. And the idea is we're checking whether M max is here. And if it's down here, then failure mode 1 can govern. Otherwise, failure mode 2 has to govern, I believe. Let me think about that for a second. 2's higher. May have made a mistake in my notes. Give me one sec. Think about this. So M max. So if it's greater, you would set this to my, and then you back work G from this equation, and then you back work F, and then you back work HEI. Okay, interesting. All right, I'm gonna fix that up. So these are my old notes, right? And I I'll tell you what the logical problem with it is. Okay, so basically we're saying HU is equal to H1, minimum of H1 and H2. Okay, so let's say H1 is 100, right, for the sake of argument, and then let's say H2 is 150. Okay, and so we know that HU is a minimum between them, right? So it ends up being 100. Okay. But now it's saying if H1 governs, right, which would be the case here, check that your maximum moment is less than the yield moment. Okay, so let's just say, again, simple numbers. Let's say the maximum moment that's applied is 50. Okay, and the yield moment is 75. Okay, so if this is the case, then HU is 100 and there's no problems. Okay, because it's less than that. But if the max moment that's applied is actually 100, now, like with my old notes, it's saying that, oh, actually the biggest moment that can be applied is 150 actually, so this should be set as 150. But that makes no sense, okay, because yeah, like it should be limited by the material property of your yield moment, right? So what I've changed it to, right? So if we get all these numbers and I move it to the other page, is this, okay? I'll tell you, these aren't just from nowhere, all right? I'll tell you where I got these from, okay? I'm also going to paste over this graph. I think it's handy. So what I'm saying is if the max moment is above the yield moment, right, you should reset it back to the yield moment, okay? That seems to make sense. So the idea is if this is 100 and the yield moment 75, well, actually we have to bump this back down to 75, okay? And then what are the repercussions of that? What does HU end up becoming? Because it becomes less than 100, like some number that's less than 100. And the way that I got that is if you go up to this step, so this is for failure mode 1, I rearranged for G, right? And I set M max as My, right? The yield moment. And then so I basically got, let's say, equation 3, and I turned it into another version of equation 3, which was rearranged for G. And then I got equation 2, and I turned it into another version of equation 2, where it's rearranged for F. And then I got equation 1, and I turned it into another version of equation 1, where it's rearranged for HU. Anyway, so that's where this comes from. So what you have to do, let me just move this. So what you have to do is you have to get G from rearranging the other equation. You have to, and then setting M max as My, and then you have to, like, so that's equation 3, that's equation 2 rearranged, and that's equation 1 rearranged, okay? And then you have to use F to find HU, okay? So that should give you a value for HU which is lower than those two ultimate moments, ultimate forces, okay? So that's the logic that I've applied for all of these final checks. So you'll see that for all these steps that are coming up, okay? So anyway, going back, let's look at fixed head conditions now, okay? So what we're doing is we're moving to here, all right? So now we're in fixed head territory, not free head territory. And we're going to look at mode 1 first, right? So this has a fairly straightforward formula because there's actually no bending involved. It's just sliding, basically, right? Sorry, that's not true. There is bending involved, and the reason is because we treat it like a cantilever, right? And the soil has like a reaction. Let's say there's a continuous spring. It's raining outside. The idea is the reaction at the cantilever is going to be formed with this equation. Yes, okay. All right, anyway, just follow these formulas, right? Okay. So now moving on to mode 2. So that was for soil failure. Now we have the case of piled yielding, but we've got one hinge, and the one hinge is at the interface between the pile and the fixed top or whatever, fixed head. Okay, and here I've drawn the distribution again. It's very similar to what you saw in the previous part, except now we've got a fixed head instead of a free head. And so, yeah, the point of rotation just has shifted. So what you do is you have to work out G, and then you work out F with G, and then you work out the ultimate horizontal load, and then you work out the maximum moment, okay? And again, we need this again later to check if your maximum moment is greater than your yield moment, okay? Failure mode 3 is where there's two plastic hinges which form, which basically ends up giving you this really strange load distribution or reaction distribution on the soil. And yeah, and then you end up with a really weird bending moment where the two yield moments lines up with where the plastic hinges are. Anyway, this can be done with a graph, right? So you find this ratio again, and that gives you this value down here on the graph. Then you find lambda L, and yeah, now we're following the restrained line. Okay, so this is important. You have to follow the dashed line now. So let's say this is, what's a good number? 10. And then let's say this is, well, you only have to input one thing, right? So you go 10. So you go from the line which says 10, you go up to the restrained line now, the dashed red line, and you go over and you get something like 10. Okay, so this ends up being 10. All right, HU, for mode 3, right, the ultimate horizontal force for mode 3 can be given with that multiplied by these constants, right? And then you can find, and then you just know that the maximum moment is the yield moment, okay? All right, final checks. Now we do the same thing again, except we have 3 failure modes, and this is for a fixed head pile. So again, you have to check that if so for the first failure mode, that's where the soil fails, and then you have to check that the maximum moment along the pile versus its length doesn't exceed the moment that causes the pile to yield. Okay, and so you do that same check thing that I talked about before, except this time we have a different formula, right? And you don't have to work out F and G and all that. This comes, like, the way that I derived this was from rearranging this equation, right? Just for HU. But I've set this equal to my, okay? You can check that yourself if you like. So that makes sense to me, okay? So, yeah. All right, next is drain conditions. So now we're in this territory here, right? And we're gonna check it for free head first, and then we're going to compare the two failure modes, right, for free head. Okay, so drain conditions, you're gonna get given the friction angle of the sand or whatever, and you have to find the vertical effective stress, and this is specifically at the base of the pile. So if that's your pile, your distribution for stress might be something like this. So this is vertical stress, right? And you're looking for this number down here. Okay, and basically the idea is that these two things, when they're multiplied together, actually gives you the horizontal stress. So horizontal stress equals vertical stress times Kp. Okay, so that's just those two things combined. And yeah, so you use all the other geometry, and then you find HU. You can find F separately. So F is the distance to the max moment along your distribution. So that's a bad example. I didn't draw the little graph thing this time. It's like basically this, right? So from the top to where the max moment is, that's what F stands for. But I didn't draw it on the side here. Okay, and then you can find the max moment because the yeah, anyway, just use this formula basically, but yeah, the stress distribution would look something like this, right? So it comes from 2/3 of this big triangle where that triangle's length. Anyway, I'm not going to try to derive this shit again. This is just from the booklet, all right? So just follow these formulas. All right, mode 2. So this is where you have pile yielding. So you find this ratio, which goes into this graph. You find the eccentricity to diameter ratio, which gives you the black line. And then you can find lambda from this graph. So I actually made up this notation because they don't have this in the booklet. It's fucking stupid. The idea is, let's say you have this yield moment ratio of 100. Oh my god, this is hard to read. That's a good one. Maybe 1,000. So say that's 1,000, and you go up to the 60 line, and then you go left, and then you find lambda 2f, right? And then that goes into this equation, and then you can find your max horizontal force. All right. So now we're checking which mode governs / what's the max horizontal. So just follows this. Similarly, I did a rearrangement to figure this out. Okay. Next is fixed head drained. So now we're here on the graph. We'll check 3 failure modes. So the first failure mode, it just follows these formulas. This is just the sliding case, so that's fairly straightforward. And that's soil failure. Mode 2, you have one hinge develop, and so now I've actually drawn the full distribution. Again, this is just for context mostly. You can literally just follow these steps and you'll get the right answer. So that gives you the max moment and the max horizontal force for failure mode 2. And then failure mode 3, similar, but we use this graph and we're following the red dashed line this time. So you find this ratio, let's say it's 100, you go up to the red dashed line, you go across, you find whatever number. This is pretty repetitive, but yeah, these are all the different scenarios you can run into. And then you plug it in here, basically. And then, and then this is the formula that I rearranged and got. So that's how to check it for a fixed head pile under drained conditions. Okay. All right. Next is lateral deflection and rotation. So now we're here. Now there's 2 different types you have to consider: uniform soil modulus, elastic modulus, or a linearly increasing elastic modulus versus depth. So for the uniform soil stiffness, that's basically over consolidated clays. Follow this rule. And if you're given elastic modulus directly in the question, then just move on to step 2. Otherwise, you should use this estimation. I'm assuming they will tell you some description of whether it's a normal or large diameter pile in the question, if they make you do it this way. So this requires you to be given CU, which you're always given, and then you can kind of approximate the soil stiffness. And then you got to find the embedment depth ratio, and then you find this new thing called a relative flexibility ratio, I guess you can call it, because it's unitless. So basically you're given in the question the elastic modulus of the pile, in other words, how stiff the concrete is. You're also given the moment of inertia of the pile, and then you're dividing that by the elastic modulus of the soil, and then multiplying it by the length to the power of 4. So a lot of the time not a lot of the time, I haven't seen that many examples, right? But EP is usually given to you in GPA, right? And then you have to convert it to MPa. So you divide it by, you multiply it by 1,000, right? So just make sure these are in the same units, basically, because the whole thing, all the units should cancel out, right? And then the soil modulus might be given to you in KPa or MPa. So just make sure they're both in MPa, and then happy days. This should be unitless. So you're going to use the table, right? to interpolate. So the idea is your inputs are the blue one and the green one, and what you're looking for are the yellow or purple ones, depending on whether you have a free head or a fixed head. Okay, so fixed head's actually pretty straightforward because only one number you need to extract. Free head, you have to find 4 numbers, but 2 of them are the exact same. So these 2 in this row are going to give you the exact same number. So you're looking for 3 numbers basically, and you have to interpolate. So it's a bit annoying because you might not be given an L to D ratio that's perfectly like 10 or 25, so you'll be able to find the number in between these 2 values depending on how far along it is. And the same thing with KR. So this is like a logarithm basically, or power of whatever. So yeah, you have to find, like, linearly interpolate between these numbers. That just comes with practice, so I would recommend doing the question and trying to do it yourself. Okay, and then next we're finding the rho. So the rho is how much it's laterally deflected at the ground level. And theta. So theta is the rotation. So the idea is that whatever you get from this formula gives you meters, and you should convert it to millimeters for the final answer. And similarly, you get radians from this formula, and so you can convert it to degrees. So we're basically inputting what we got. So if you got a free head, you found 4 numbers, right? And then you plug it in 1, 2, 3, 4. And you're putting in H and M and all these other things. Be pretty careful with the power, the power of L. I've done it in red because it's pretty easy to miss. They'll also change when you have got a fixed head at the top. So here it's 1, 2, 2, 3, 1. You'll see later. This all gets bumped up a power later. If you have a linearly increasing soil modulus, basically. So for normally consolidated clays or sands, right, you're going to be following these set of rules, right? So we're here in the map. So if you have basically if NH is given, so NH is the rate at which EC increases per meter into the ground that you go. If you're given it in the question, then just use it. Otherwise, you should use this table. So you figure out what you have based on the description in the question. Okay, and then you find the L to D ratio, you find Kn. So Kn is similar to Kf, I think it was called. Kr, sorry. So it's the relative flexibility of the pile, but now it's in the context of when you have a linearly increasing elastic modulus. Now what's changed here is this is no longer to the power of 4, it's to the power of 5. And this is in MPa per meter units, okay? So just make sure you've got everything. This should still end up being unitless in the end. Use the table. That's your unitless number. That's your other input. And you just do the same thing. So all of these have a dash in them, right? So it's like influence factor or whatever, right? So I for influence, and then dash, and then whatever. You're going to find all these values. And yeah, and then you do the same step at the end, except now, before all these powers were less by 1, all the powers for L, so it was 1, 2, 2, 3. Now it's 2, 3, 3, 4. So just be careful. The reason for that is because NH is basically your elastic modulus divided by meters, right? So we have to have an extra L in order to keep it dimensionally consistent. All right, anyway, so those are all your formulas. Okay, and then here's a worked example. Sorry, I'm not really going to go through it in depth, but you should do this in your own time before your exam on Friday, because I feel like there's a good chance that horizontal loading on piles is in your finals, because the lecturer talked about it. And yeah, essentially, like, there's a lot of different scenarios or different cases, but all of them are pretty easy, such that they don't take very long. It's you have to identify what you have to do in all the different cases, right? And so just follow the working. You can figure out the ultimate capacity and the horizontal displacement of these of these piles. So yeah, good luck with that, and we'll start recording.